Dobar dan. A very good evening to one and all. My topic is discussion on two alternative approaches to CT coupon-based K1C determination, providing results comparable with ASTM E399. Myself, Parthasarathy Iyengar, is an M&P engineer specializing in aluminium alloys at Airbus in the UK, based in Filton at the AirTech facility. My collaborators on this piece of work who are not present here are Mr. John Mardaras, who is an FNDT methods expert, metallic method FNDT expert based in Airbus in Toulouse, and Dr. Shwe, who is associate professor with the University of West of England. Now, this is not quite a detailed work with regards to a lot of modeling or experiments, but is philosophical in nature based upon observations over the years. There is always, obviously, some experimentation involved, some testing involved. Can't do without it. I'd like to express our sincere gratitude to Mr. Bob Haldane from Arconic, Kidscreen, who was kind enough to provide us with some material from their facility, bespoke aluminium 2024 T351. Since I come from the aerospace industry, we do tend to use it just a little bit and carry out some testing for us. And we do appreciate his mindset of learning by trial, which is what has essentially grown industry over the years. I'd also like to express my gratitude to my colleague, Dr. Mustafa Volkanuz, who is an expert in fracture mechanics based in Airbus in Bremen. So we'll talk about the objectives, provide an overview and background of fracture toughness testing as per the ASTM E399, so we're focusing on CT specimen. Take a look at a new concept called, it's actually an old concept, but formalized recently within the ASTM E399 called the K1SI, and look at an alternative type of testing, cylindrical bar specimen, and then finally a discussion. The objectives and limitations, well, primarily, we're on about, this is where we're limited to, because I work in aluminium and light alloys, we're going to limit this discussion to certain aircraft-based aluminium alloys, which are largely 2000 and 7000 alloys. That's what I'm allowed to work on generally for the most part. We will leave aluminium lithium out of this for the moment. And we will cover another standard for the ASTM for aluminium alloys, which is the B645 as well, as part of this, because it provides some relief in compliance compared with the ASTM E399, but the method is generally the same. Alternatives considered are obviously K1SI and cylindrical bar specimen, as I said, and my goal is really to present discussion and a question to yourself: what is fracture toughness to you? Incumbent validity criteria are ignored as part of the discussion. When I say incumbent validity criteria, I am referring to what the method says they are. So here's just some images. Background, why am I doing this? Airbus have in 2020 announced 0E. We're looking at the use of hydrogen aircraft, both by direct combustion and by use of fuel cells. Direct combustion involves the use of cryogenic hydrogen. And this will, regardless, materials will come across it. We will need novel testing methods to get into it. We are, along with industry, working on means of cryogenic testing and testing with hydrogen. There is a requirement to prove in production the quality of raw material that is produced. And we will focus on K1C, however, in this presentation. So we'll use 2024 in this as our baseline because of its relevance, because of its, let's say, easy access to data. In here, we've got some MMPDS data. MMPDS has generally been used as a basis for data, because it is open source and it is an industrial frame of reference. Comparing 2024 T351 couple of steels, you can see the difference in elongation. For example, you've got 12% for 2024. You've got steel, certain stainless steels, which will go to 40%. Some that wouldn't quite elongate as much, then you go to 10%. There's also aluminium 2219 in the T8 condition, which only goes to 7%. However, the E399 method, now it must be said, is quite old. It came out in the 60s. Was originally for brittle materials, ceramics. Started with Griffith and was about linear elasticity. So initially, they'd included, it was seen that you could test certain elastic materials where the elasticity was low. But as you're starting to grow elasticity, what then? Also note that the MMPDS values, just for reference further down, is 34.06 MPa root meter, with a minimum of 29.66 MPa root meter for 2024 T351. We'll note from this image that while the steels to the left is, these are your elongations for steels, your aluminium is at about 13% to 2024. And these are real curves provided to us by Arconic. It's a photograph, so apologies if it was a quick one upon request, in the L and LT direction. So in reality, while your expectation is for it to be at about 13%, goes to about 21% there, 18% there. Your yield point is about there. If you talk about true linearity, it is about somewhere about there. And note that the linear portion of stress strain curves extends to nearly 2/3 of the yield point. 2/3 of the. So fundamentally, what is fracture toughness with a CT specimen? When a pre-crack specimen or component is monotonically loaded to fracture, crack extension begins, and it begins macroscopically flat, but is immediately accompanied by small shear lips. We don't see them in this little sketch here, but this does come from a famous book, which is Eols and Van Til. Mode 1 fracture toughness is commonly applied to design of metallic parts or interrogate production quality in industry. Our curves are generally applicable where the ratio, we say, is a minimum of, say, length to width over thickness is over 100. And K1C on the apply, by contrast, is applied commonly where this above generalization, which is stated, is not met with. K1C is a linear elastic measure of the value of the applied crack tip loading at which the crack grows under a defined length, under high constraint, and without deformation in the thickness. These are 70-10 specimen, and you can see what an ideal fracture toughness specimen, when it's ideally failed, all compliant, should look like. There's a pre-crack here. You can see that this is almost symmetric. This is quite brittle here. There are small shear lips here. You can see like a dark line. You can see a negative here, and you can see the positive here. These are quite thick specimens. They're like 40 mil or 35 mil. Irrespective of material, 399 does constrain the geometry. For example, the width is 2 times the thickness. B is the term used for thickness within E399, with some conditional allowance. So there are some other terms which can be met with to not precisely conform to this geometric requirement. Typically, specimen is pre-cracked and then pulled apart. Fracture toughness test is applicable for both structural design and production quality assurance. Although essential, conventional testing is premium on cost and resource. The notch is quite expensive to cut along with geometry. It needs to be very precise. And there's some images of, examples from aircraft. If your specimen gets small now, that ideal image that I showed you just before is a little bit different to that. Fracture toughness tends to rise during crack extension and is a function of a stable crack growth length against a certain load. It has been indicated that under plane strain conditions, a hinge type deformation is followed by a flat fracture, whereas under plane stress, a slant fracture occurs by shear after a hinge type initiation. Now, this is an MT specimen or a CCT specimen. This is also an image of Eols and Van Til. This is some experimental data. Say we got a certain extrusion, and from the same extrusion thickness, based on specimen size, varying specimen size, we are getting different results. And while I'm not allowed to show you the numbers there, I can tell you that the range in value of fracture toughness is quite large, quite significant. This is an example of what we call a cranked extrusion. You can see the twist there. It's made like that. And you're required to extract fracture toughness from something like that. And it's quite thin. This is a forged part. It's actually something that was forged and then precision machined. If it was closed die forged. So if you've seen a closed die forging, that will look like a bit of a bluff version of this, of the shape that you see. Certain products, such as profiled extrusions and die forgings, are often size limited. So the room to extract specimen from there is limited. So you can't get thick specimen to obtain large enough, an ideal fracture. You might end up with things like this, or a bit more complicated as it gets really thin. So K1SI was introduced based on an old concept by an academic called Wallen. It actually came out since 1976. That's when the original publication was. But K1SI was only formalized in E399 in 2023, I believe, as part of ASTM E399. It is based on a fixed amount of crack extension of 0.5 millimeter. And as a result, is less sensitive to specimen size than the K1C. This is what the claim is, whose force displacement test record can be reinterpreted to calculate K1SI. So you perform a normal K1C test, and you draw your 95% secant line, get your K1SI, your K1C, but you recalculate your secant line for K1SI based upon that relationship, which is provided within the E399. And W minus A, which is the width minus A being the crack length, is your parameter that will define the percentage of where your secant length lies. These are this is your typical types of R curves that you can get. So you can be a type 1, type 2, or type 3. Type 1 is what we see most commonly in aluminium alloys. With 2024 specimen where, thickness of 19 mil to 21 mil, we did some testing. This was specimen provided to us by Arconic, all taken from a 25 millimeter plate. We found that K1SI is generally seen to be in the vicinity of 3 MPa root meter from the corresponding KQ values. So doesn't really make much of a difference. And surprisingly, we also noticed another thing, which was just a corollary, really. Bob chose to change the preferred ratio, where there is a constraint between width and thickness within the E399. And there's certain conditions by which you can override it, but you can't override it beyond a certain point. Regardless, Bob decided that we should probably make specimen that were longer than allowed by E399. And guess what? The results we found was that it didn't really make a difference to the answer for aluminium 2024. Similar observation was made with a CT specimen which was a lot thinner. It was only about 13 millimeters thick on 2026. This was some internal effort we did. Not allowed to publish the results yet. incumbent K1SI procedure requires a valid K1C test specimen. So you can't skip the validity requirements. Now, what are the validity requirements? Validity requirements in this case, if I haven't already made clear, is the type of surface, the type of fracture that is expected from the ideal. So apologies for going back a little bit. That kind of fracture, that is your ideal fracture. And there's some measurements that are made to the fracture surface. And if they're not compliant, then your test is invalid. So you'll have to repeat a test. And this is an expensive affair. So we'll go look at another alternative, cylindrical bar specimen. We came up, this idea was proposed a few years ago and was actually presented in ECF 11, except cylindrical bar specimen were pre-cracked. We revisited it, took it a step further. And instead of presenting pre-cracked specimen by Sarchami and Burns, as they did, their former colleagues of ours, we just machined, we just turned specimen in a lathe. We turned them in a lathe and cut a notch and decided to look at it. Now, looking at your standard tensile specimen, a normal tensile specimen, aluminium, you will see a typical 45-degree break. You'll see some ductility there. Compare that with a notch failure, you see something that is quite brittle. Now, what we did here is we applied an elastic dye, which is basically orange tack. It will settle on the negative, on any negative surface, which is in the circumference. And you can see it, you can see that here. You can see that it hasn't settled in the middle. This is more brittle. You can see some ductility around the circumference of this. That's basically what the specimen looked like. I've got them in my bag if someone would like to take a look at a couple of them. We tested 10 mm and 8 mm dia NRB specimen. Not a lot of them. So we'd like to test generally about 30 of them before we present data. So we haven't put them on the statistics, but I can give you a quick overview. So that's what we took, the force displacement record, just from, as in you would do from a tensile test. And we just decided to, this is from an 8 mm specimen, took the linear, the end of the tangent, end of the tangent of the curve, of the linear portion of the curve, and marked that as a load and calculated a stress intensity based upon a formula by Wang. This gives you a value that is actually within range of the K1C value for the material. In this case, we got a K1C, I'll just call it a KNRB or a type of KQ of 31.5 MPa root meter. Yes, you do see some ductility in the around the fringes, while the center of it is shown to be brittle. We have got to establish some certain specific conditions around which test is valid, but the principle is that there is a simplistic way of manufacturing specimen and obtaining a value that is representative of the K1C value, we believe. Now, question to you is, could dimensional control be less rigorous, be inspected and documented with modern microscopy? We think yes, because there's cameras, and in the scheme of things, microscopes, optical microscopes are not that expensive. To conclude, a little bit of a discussion. This is, by the way, 2026 CT cracked surface. This is what it looks like. This is from a very thin specimen. It's from a 12.7 millimeter specimen. This is a quick view of some of our round specimen. Presented proposals arrive with a mindset of continuity development and simplification. We are not looking to question existing theory or practice, but we are looking for a mindset change with regards to what could be applied as acceptable quality from a production testing perspective, and also from a future aircraft perspective, because as materials, now there's another standard for which can actually test thin material, which is called the E740. E740, it does part-through crack, and you can apply a factor and basically knock it down to be in line with a said K1C value for a given material. But that doesn't reduce the rigor of testing. That is still the same as your conventional E399 CT. Indicative values for semi-ductile NRBs may be developed to assess material quality in serial production. And there was now an ASTM standard for notched round bars, believe it or not. It was called the E602. It was withdrawn for some reason. We'd like to propose possibility of reinstatement, or could a new EN standard be created? And we'd like to ask for your interest. Would anybody be interested in independently testing the concept of round specimen, of notched round bars, and producing data for various materials for an equivalent to K1C? So basically perform it, produce it, test it, and compare it with a K1C value. Thank you.